In this lecture, we're going to learn a new way of representing the electronic configuration. It's basically the same electronic configuration that we discussed earlier. So in this representation, you would be given boxes, and each box would be representing an orbital. So for example, in sodium's case, the electronic configuration, there are 11 electrons. So that means there are 2 electrons in the 1s subshell, 2 electrons in the 2s subshell, 6 electrons in the 2p subshell, and 1 electron in the 3s subshell. So you're going to write exactly the same electronic configuration. Remember, this is the lowest energy subshell, and as you move further away, the energy of the subshells keeps on increasing. So each subshell would be represented by the boxes as shown over here. So this axis over here is the energy axis. This orbital over here is going to be the lowest energy orbital. So I'm going to label them first. The first one is the 1s orbital. After that, you have the higher energy orbital would be the 2s orbital. So this box over here is the 2s orbital. Then you have the 2p subshell, which has 3 orbitals. So this would be 2px, and this would be 2py, and the third one would be 2pz. And the last, in this particular case, there are 4 subshells. So this last one would be the 3s subshell. So this is the 3s subshell. Now I'm going to fill the electrons, and each electron would be represented by a spin. It would either be upward or downward. So each electron would be represented by a spin. So the 1s orbital is full. So there's going to be 1 electron in the upward spin. The other one would be in the opposite spin, which would be the downward spin. The 2s subshell also has 2 electrons. So 1 electron in the upward and 1 in the downward. The 2p subshell is also full. So I'm going to fill 6 electrons in this. So first they would be filled in a single manner first, after which an oppositely paired spin electron would fill the orbitals. So this 2p is completely full. The 3s only has 1 electron, so that would be an upward spin. So as you can see, the electronic configuration of sodium can also be represented by this diagram over here, which basically means the exact same thing, except that you are clearly showing the spin. This is the 1s orbital, this is the 2s orbital, these are the 2p orbital, 2px, 2py, and 2pz, and this is the 3s orbital. 2 electrons in this, 2 electrons in this, a total of 6 electrons in the 2p subshell, and 1 electron in the 3s orbital. So it's exactly the same electronic configuration. Now in exactly the same way, I'm going to write oxygen's electronic configuration, which has 8 electrons. So the conventional electronic configuration would be the 1s subshell would have 2 electrons, the 2s subshell would have 2 electrons, so that's a total of 4 electrons. And after that, you have the 2p subshell that would have 4 electrons. Now I'm going to try and fill these electrons in the subshells and the orbitals that I've drawn over here, the boxes that I've drawn over here. So starting with, I'm going to start off with the 1s subshell that has 2 electrons, so 1 upward spin, 1 downward spin. After that, I have the 2s subshell, so 1 upward spin and 1 downward spin. Now the 2p subshell has 4 electrons. So I'm going to fill the orbitals in a single manner first. So I'm going to try and fill 4 electrons. The first electrons would be filled in a single manner first. And now the 4th electron would have an oppositely paired spin. So that's a total of 4 electrons in the 2p subshell. So that's 2p4. So this would be the electronic configuration if I try to fill the boxes over here and represent the same electronic configuration, but this time using this diagram over here. In my next example, I'm going to try and write the electronic configuration of a bigger atom and try to fill the boxes. The same thing represented by boxes over here, each box representing an orbital. So iron has 26 electrons, so the electronic configuration would be 1s2, 2s2, 2p subshell would have 6 electrons, then you would have 3s2, then 3p6, then the 4s subshell gets filled, and the last 4d has a total of 6 electrons. So I'm going to write this electronic configuration in the boxes below. So the 1s, the lowest energy, has 2 electrons, so that would be represented by 2 arrows having opposite spins. The 2s subshell has 2 electrons, so that would be represented by 2 arrows, 2 electrons having opposite spin. The 2p is completely full, so first they would be filled in a single manner, each orbital getting 1 electron, and then the oppositely spin electron having opposite spin would then enter each of the orbitals, and that would make all the orbitals paired. The 3s is completely full as well, so that's 2 paired electrons having opposite spins. The 3p is completely full as well, so 1 electron entering each orbital first, and then the ones having opposite spins. And after that you have the 4s that is completely full, and then the 3d has 6 electrons. Now there are 5d orbitals, so 1 electron goes into each of the 5d orbitals, so you have 1 electron each, and that each orbital getting 1 electron first, getting filled in a single manner first. Now I have to fill 6 electrons, so there are 5 electrons already there. So one of the orbitals would be paired, it would have another electron. So that's the electronic configuration of iron. Now one thing that you would notice as well is that the orbitals and the subshells according to energy levels, you would notice that the first few subshells, they have a very large gap in energy. And as you move away from the nucleus, the gap between energy levels of the electrons keeps on decreasing. So there's lesser gap between 2p and 3s. The 3s and 3p has even lesser gap. The 3p and 4s subshells have even lesser energy gaps. 3d and 4s also has lesser. So as you move away from the nucleus, and subshells further away from the nucleus are going to have very less differences in energy levels. So this would come in handy when you're losing electrons. For example, transition metals, what happens to them is that the d orbitals and the 4s orbitals have very little gap in energy levels, which is why they can lose electrons from the d subshell, and they can also lose electrons from the 4s subshell, because the difference in energy levels between the electrons is very little. But that is not the case for smaller atoms, because the 2s and the 1s and the 2p and the 2s, the energy gap is very different. It's very large, so electrons are generally lost from the outermost shell. But for transition metals, electrons could be lost from multiple subshells, as the 3d and the 4s, they don't have much energy difference between them.